straight line graphs, the gradient doesn't change. Okay, so the example up above, it's just 2 the whole time. Now this one here, if I was to look at this particular position on the graph, I'm looking at this particular value of x. Okay, how would we look at the gradient at this particular place? Well, we would draw a tangent to it, and we would be able to find the rise and run. Now tell me something about this gradient.
It's positive.
It's positive. Excellent. Tell me something else about the gradient.
It's steep.
It's steep. Okay, so we would be looking for a relatively high number, and it's a positive number. Okay, and that's for this value of x. But if we were to look at this point on the graph, we're now looking at this new value of x. Tell me something about the gradient here. Again, we would draw a tangent. What does my tangent look like?
Straight line.
Straight line. What kind of line? Horizontal. What does that tell us about the gradient at this point?
0.
0. Okay, so this would be a 0 gradient. How about this? Oh, let me go over here in the positive. How about this place here? We're looking now at this positive value of x. It's now negative, and it's pretty steep, not humongous, but quite positive, negative, quite a big negative number. All happy? So we can see that it changes as the graph changes, and it changes depending on the value of x. So, let me look at my writing here. So the gradient is different at each value of x. An approximate answer would be to draw a tangent, so that's what I've just said here. But we don't want to have to do that all the time. We want to try and find an easier method. And so what we will be doing is we will be finding what we call the derivative. Okay? The process, one of the processes in calculus is called differentiation. And when you differentiate something, you end up with the derivative. And this derivative will allow you to tell me what the gradient is at any given value of x. Okay? Right, so drawing tangents to find gradient is very tedious, so we need to find an easier way. So in these cases, we would use calculus to find an expression. Now, be aware that some people start to get confused. The derivative is an expression, okay? So it will have x values in it. And the reason is, as we just said, that at different values of x, you're going to get a different answer, okay? So our expression, our derivative, has the x in it. You then substitute your value of x to find the actual numerical value, okay? So that's what I just said there. Oh, shush now. All right, so the rule for differentiating. So we talked about this. Remember, you did learn it last year. So what was the rule for differentiating? What do we have to do?
Something over y over dx.
It's going to be called dy over dx, yeah? But how do we actually do it? What's the process? We just talked about it. Power goes to the front. And good. Subtract 1 from the power. Okay, that's essentially what you need to know. So you're going to, the power comes in front, and then you subtract 1 from the power. Now, when we bring the power to the front, what are we actually doing to it? It's becoming multiplied. Yeah. Okay, so we're going to come across some examples, but in some cases there's already a number there. So if there's already a big number there, then that power doesn't just sit next to it, you actually do multiply it by it. So using that rule, the power coming in front and taking 1 off the power, if this was my expression here, y equals x cubed, what would my derivative be? 3x squared. Super cinchy. Okay. Good time to write that. Okay, so now we've talked about dy dx. Yes, so we talked about that when we did first principles. But there are other ways of showing that something is being differentiated. So if your original expression starts with a y equals, which is what this one up here did, we would say dy dx represents the derivative. Okay. Some cases it will have fx equals. Remember, that's in function notation. to show we're differentiating that expression, we would write f dash x. Okay? So this is dy dx, this is f dash x. Both show that it's the derivative. The process, the method that you're using doesn't change, it's just what you call it. Okay? One thing I do want to make clear is that this f dash x is not f minus 1x. Okay, sometimes people get confused with that. What did the f minus 1x tell us?
Inverse.
The inverse. Good, that's the inverse. Okay, so don't get confused. F dash means you're differentiating, or it's the derivative. F minus 1 is the inverse function. Right, so as I said, sometimes there could be a coefficient or a number in front of the x term already. If that's the case, then we're just multiplying our power by that. So for this example here, we've got y equals 3x to the power 5. So I'm going to show that I'm differentiating. So I'm going to write dy dx. And what's the rule? Power goes in front, take one off the power. So I'm going to have 5 multiplied by 3x now to the power 4. Now obviously we wouldn't leave it like that. What would we then write? 15x to the power 4. Now you would probably start to go straight to this option here. Okay, you don't have to write 5 times 3x to the power 4. You're going to get so proficient at it that you'll just be writing 15. But just be aware, this is your notes, it's your first example like this, so I'm just writing it like this for this one. In a similar way to the fact that sometimes there's a coefficient, very rarely will there just be one term. Most of the time we will have several terms in an expression. So we would just differentiate one by one. So this was y equals, so we're showing our derivative is dy dx. So Cameron, what would my first term be?
4x.
Lovely. Olivia, what's my next one?
Sometimes
6x. About 2, good. Notice that my negative sign belongs to it still. Okay, so it subtracts 6x squared. And Skylar, what's my last one?
2x.
Nice. Okay, easy peasy. Now, we're asked to differentiate a term with just an x. Okay, so it's just got an x. It's no different. The process is exactly the same, but I want to just go through it in a long-winded way just so you can see how we can speed it up. Oh, hang on a minute.